In the last video, I had this 2 by 3 matrix A right here, and we figured out all of the subspaces that are associated with this matrix. We figured out its null space, its column space. We figured out the null space and column space of its transpose, which you can also call the left null space, and the row space, or what's essentially the space spanned by A's rows. But let's write it all in one place, because I realize it got a little disjointed, and see if we can visualize what all of these look like, especially relative to each other. So let me copy and paste my original matrix. Copy. And then let me scroll down here and paste it over here. Edit, paste. Let me see if I can find our key takeaways from the last video. So our column space right here of A was this thing right here. Let me write this. This was our column space. It was the span of the R2 vector 2, 4. We copy that. Copy that. Bring it down. Paste. This was our column space. Let me write that. This is the column space of A was equal to that right there. And now what other things do we know? We know what we know that the left null space was a span of 2, 1. Let me write that. So our left null space, or the null space of our transpose, either way, it was equal to the span of the R2 vector 2, 1. 2, 1. Just like that. And then what was our null space? Our null space, we figured it out in the last video. Here it is. It's the span of these two R3 vectors. Let me copy and paste that. So that's edit, copy. Let me go down here. Let me paste it. So that was our null space right there. And then finally, what was our row space? What was our row space, or the column space of our transpose? The column space of our transpose. So the column space of our transpose was the span of this R3 vector right there. So it's this one right here. And so let me copy and paste it. Copy and scroll down, and we can paste it. Just like that. Just like that. Okay, let's see if we can visualize this now that we have them all in one place. So first of all, if we imagine a transformation, x that is equal to A times x, our transformation is going to be a mapping from what? X would be a member of R3, so R3 would be our domain. So it would be a mapping from R3, and then it would be a mapping to R2, because we have two rows here, right? You multiply a 2 by 3 vector, a 2 by 3 matrix times a 3 by 1 times a 3 by 1 vector, and you're going to get a 2 by 1 vector. So it's going to be a mapping to R2. So that's our codomain. So let's draw our domains and our codomains. So you have, well, I'll just write them very generally right here. So you can imagine R3 is our domain. And then our codomain is going to be R2. It's going to be R2 just like that. Codomain. And our T is a mapping, or you could even imagine A is a mapping between any vector there and any vector there when you multiply them. Now, what is our column space of A? Our column space of A is the span of the vector 2 minus 4. It's an R2 vector. This is a subspace. This is a subspace of R2. We could write this. So let me write this. So our column space of A, these are just all of the vectors that are spanned by this. We figured out that these guys are just multiples of this first guy, or we could have done it the other way. We could have said this guy and that guy are multiples of that guy. Either way, but the basis is just one of these vectors. We just had to have one of these vectors. And so it was equal to this right here. So the column space is a subset of R2. And what else is a subset of R2? Well, our left null space. Our left null space is also a subset of R2. Our left null space is also a subset of R2. So let's graph them actually. So I won't be too exact, but you can imagine let's see, if we draw the vector 2, 4, let me draw some axes here. Let me scroll down a little bit. So if you have some vector, let me do this as neatly as possible. It's my vertical axis. That is my horizontal axis. And then what does the span of our column space look like? What does the span of our column space look like? So you draw the vector 2 minus 4. So you're going to go out 1, 2, and then you're going to go down 1, 2, 3, 4. So that's what that vector looks like. That's what that vector looks like. And the span of this vector is essentially all of the multiples of this vector. You could say linear combinations of it, but you're taking a combination of just one vector, so it's just going to be all of the multiples of this vector. So if I were to graph it, it would just be a line. It would just be a line that is specified by all of the linear combinations of that vector, right there. This right here is a graphical representation of the column space of A. Now, let's look at the left null space of A. Or you could imagine the null space of the transpose. They are the same thing. You saw why in the last video. What does this look like? So the left null space is a span of 2, 1. So if you graph 2 and then you go up 1, is the graph of 2, 1. It looks like this. Let me do it in a different color. So that's what the vector looks like. The vector looks like that. But of course, we want the span of that vector. So it's going to be all of the combinations, or all you can do when you combine one vector is just multiply it by a bunch of scalars. So it's going to be all of the scalar multiples of that vector. So let me draw it like that. It's going to be like that. And the first thing you might notice, let me write this. This is our left null space of A, or the null space of our transpose. This is equal to the left null space of A. This is equal to the left null space of A. And actually, since we wrote this in terms of A transpose. It's the null space of A transpose, which is the left null space of A. Let's write the column space of A also in terms of A transpose. This is equal to the row space of A transpose. Right? If you're looking at the columns of A, everything it spans, the columns of A are the same things as the rows of A transpose. But the first thing that you see when I just at least visually drew it like this is that these two spaces look to be orthogonal to each other. It looks like I drew it in R2. It looks like there's a 90-degree angle there. And if we wanted to verify it, all we have to do is take the dot product. Well, any vector that is in our column space, so any vector, you could take an arbitrary vector that's in our column space, it's going to be equal to C times 2 minus 4. So let me write that down. So any vector here, so if V is a member, I want this stuff up here. I'll scroll down a little bit. So if V, let's say V1 is a member of our column space, and that means that V1 is going to be equal to some scalar multiple times the spanning vector of our column space. So some scalar multiple of this. So we could say it's equal to C1 times 2 minus 4. That's some member of our column space. Now, if we want some member of our left null space, right? Let's write it here. So let's say that V2 is some member of our left null space. V2 is some member of our left null space, or the null space of the transpose. Then what does that mean? That means V2 is going to be equal to some scalar multiple of the spanning vector of our left null space of 2, 1. So any vector that's in our column space can be represented this way. Any vector in our left null space can be represented this way. Now, what happens if you take the dot product of these two characters? So let me do it down here. I want to save some space for what we're going to do in R3, but let me take the dot product of these two characters. So V1 dot V2 is equal to, I'll arbitrarily switch colors, C1 times 2 minus 4 dot C2 times 2, 1. And then the scalars, we've seen this before. You can just say that this is the same thing as C1, C2 times the dot product of 2 minus 4 dot 2, 1. And then what is this equal to? this is going to be equal to C1, C2 times 2 is 4, and then plus minus 4 times 1, minus 4. Well, this is going to be equal to 0. So this whole expression is going to be equal to 0. And this was for any two vectors that are members of our column space and our left null space. They're orthogonal to each other. So every member of our column space is going to be orthogonal to every member of our left null space, or every member of the null space of our transpose. And that was the case in this example. It actually turns out this is always going to be the case, that your column space of a matrix, its orthogonal complement is the left null space, or the null space of its transpose. I'll prove that probably in the next video, either the next video or the video after that. But you can see it visually for this example. Now, let's draw the other two. Let's draw the other two characters that we're dealing with here. So we have our null space, which is a span of these two vectors in R3. It's a little bit more difficult to draw it. These two vectors in R3 right there. But what is the span of two vectors in R3? All of the linear combinations of two vectors in R3 is going to be a plane in R3. So I'll draw it in just very general terms right here. If we draw it in just very general terms, let me see. So let's say it's a plane in R3. It's a plane in R3 that looks like that. Maybe I'll fill in the plane a little bit, give you some sense of what it looks like. This is the null space of A, and it's spanned by these two vectors. You could imagine these two vectors look something like, I'm drawing it very general, but if you take any linear combinations of these two guys, you're going to get stuff, any vector that's along this plane that goes infinite directions. And of course, the origin will be in these. All of these are valid subspaces. Now, what does the row space of A look like? Or you could say the column space of A transpose. Well, it's the span of this vector in R3. But let me show you something. Well, let's see something interesting about this vector in R3. How does it relate to these two vectors? Well, you may not see it immediately, although if you kind of look at it closely, it might pop out at you that this guy is orthogonal to both of these guys. Notice, if you take the dot product of 2 minus 1 minus 3, and you dotted it with 1/2, 1, 0, what are you going to get? You're going to get 2 times 1/2, which is 1, plus minus 1 times 1, which is minus 1, plus minus 3 times 0, which is 0. So that's when I dotted that guy with that guy right there. And then when I take the dot of this guy with that guy, what do you get? You get 3/2, 0, and 1 dotted with, let me scroll down a little bit. Don't want to write too small. Dotted with 2 minus 1 minus 3. In the columns, the row space of A, I wrote the spanning vector there. I wrote the spanning vector there this time. I probably shouldn't have switched the order, but here I'm dotting it with this guy, and then here I'm dotting it with this guy right there. So if you take it, 3/2 times 2 is equal to 3, plus 0 times minus 1 is 0, plus 1 times minus 3 is minus 3, so it's equal to 0. So the fact that this guy is orthogonal to both of these spanning vectors, it also means that it's orthogonal to any linear combination of those guys. Maybe it might be useful for you to see that. So let's say that let's take some member of our null space. So some member of our null space. So let's say that V3, let's say the vector V3 is a member of our null space. That means it's a linear combination. It's a linear combination of that guy and that guy. Those are the two spanning vectors. I had written it up here. These are our two spanning vectors. But I need the space down here, so let me scroll down a little bit. These are the two spanning vectors. So that means that V3 can be written as some linear combination of these two guys that I squared off in pink. So let me just write it as maybe A times 3/2, 0, 1 plus B times 2B times 1/2, 1, 0. Now, what happens if I take the dot product of V3, if I take the dot product with V3, and I dot it with any member with any member of my row space right here. So any member of my row space is going to be a multiple of this guy right here. That is the spanning vector of my row space. So let me actually create that. So let me say that V4 is a member of my row space, which is the column space of the transpose of A. And that means that V4 is equal to, let's say, some scaling vector. Well, I use C a lot. Let me use D. Let's say it's D times my spanning vector. D times 2 minus 1, 3. So what is V3, which is just any member of my null space, dotted with V4, which is any member of my row space. So what is this going to be equal to? This is going to be equal to, this guy. So let me write it like this. A times 3 halves, 0, 1, plus B times 1 half, 1, 0, dotted with this guy, dot D times 2 minus 1, 3. And what is this going to be equal to? Well, we know all of the properties of vector dot products. We can distribute it and then take the scalars out. So this is going to be equal to, I'll skip a few steps here, but it's going to be equal to AD times the dot product of 3 halves, 0, 1, dot 2 minus 1, 3. Just distribute it out to here, plus BD times the dot product of 1 half, 1, 0, dotted with 2 minus 1, 3. This is a dot product. I just distributed this term on these two terms right here. And we already know what these dot products are equal to. We did it right here. This dot product right here is that dot product. I just switched the order, so this is equal to 0. And this dot product is that dot product. So this is also equal to 0. So you take any member of your row space, and you dot it with any member of your null space, and you're going to get 0, or any member of your row space is orthogonal to any member of your null space. And I did all of that to help our visualization. So we just saw that any member of our row space, which is the span of this vector, is orthogonal to any member of our null space. So my row space, which is just going to be a line in R3 because it's just a multiple of a vector, is going to look like this. It's going to look like this. It's going to be a line, and then it's going to maybe go behind it. You can't see it there. It's going to look like that, but it's going to be orthogonal. So let me draw it like so. This pink line right here in R3, that is our row space of A, which is equal to the column space of A transpose, because the rows of A are the same thing as the columns of A transpose, and the row space is just the space spanned by your row vectors. And then this is the null space of A. This is the null space of A, which is a plane. It's spanned by two vectors in R3. Or we could also call that the left null space of A transpose. And I never used this term in the last video, but it's symmetric, right? If the null space of A transpose is the left null space of A, then the null space of A is the left null space of A transpose, which is an interesting takeaway. Notice that you have here the row space of A. The row space of A is orthogonal to the null space of A. And here you have the row space of A transpose is orthogonal to the null space of A transpose. Or you could say the left null space of A is orthogonal to the column space of A. Or you could say the left null space of A transpose is orthogonal to the column space of A transpose. So these are just very interesting takeaways in general. But this shows you, and just like I said here, that look, these happen to be orthogonal, these also happen to be orthogonal, and this isn't just some strange coincidence. In the next video or two, I'll show you that these are actually, that this space, this pink space, is the orthogonal complement of the null space right here, which means every vector in that is orthogonal to or it represents all of the vectors that are orthogonal to the null space. And these two guys are orthogonal complements to each other. They each represent all of the vectors that are orthogonal to the other guy in their respective spaces.